the most recent Modular Open Systems Architecture workshop that we had just hosted for the Systems Engineering Research Center, and also apologize for the confusion. I know we had conflicting dates where this SERC talk was going to occur on the same day as that workshop. So without further ado, it's my extreme pleasure to introduce Dr. Gary Witus of Wayne State University to present his work in MOSA and his talk on what lives at the intersection of MOSA and SetBased Design. So Gary, I'll turn it over to you. And if anyone has any questions for those who are dialed in and not able to access WebEx, please email your questions to me. That would be Mitchell Kerman, so it's M. Kerman, K-E-R-M-A-N, at Stevens, S-T-E-V-E-N-S, .edu. I will take your questions. I will make sure they get posted in our WebEx question and answer section as well, so Dr. Witus sees them and can address them as well. So Gary, the floor is yours.
Okay, thank you, Mitchell. So for those of you who cannot see the WebEx, I will talk through the I'll keep track of which chart we're on. Right now we're on the introductory chart, and I am now paging down to the disclaimer, chart number 2, and chart number 3. And so what I wanted to do was to start by setting a little bit of the context, which we discussed in the MOSA workshop a week or so ago. And I think that the real framing perspective is the 5 general benefits that DoD is hoping to get from MOSA. And the reason I want to review these, because as we go through some of the exercises and attempts to try and develop and implement MOSA implementations, I want to keep coming back to SERC or systems engineering research challenges, and a lot of the research challenges will point back to the DoD anticipated DoD benefits. So scattered throughout this talk, as we hit some of the observations and experiences, then I want to cast forward some systems engineering challenges, and I hope that people both on the researcher side and on the DoD consumer of the research side will will consider which of these what they see as important and what they see as further issues or research directions from these challenges. So we can all read the chart, but what I want to emphasize out of these 5 benefits is that they're occurring at different stages of the acquisition life cycle. And so when we're talking about improving interoperability, that's both interoperability in the development, so we get open interface definitions, but it's also open operational flexibility and interoperability between components that share modules. So that's much later down in the acquisition life cycle. And similarly, enabling technology refresh is not when we're on a new start, but it's on system upgrades. Increasing competition comes back to the beginning of the, or not the beginning, but the kind of middle of the life cycle in engineering and manufacturing development. Cost savings. It's interesting when we look at this because the goals here are talking about the total cost of ownership and reuse over the life cycle. So we're really looking at the full system costs, and not necessarily reducing the cost of development, because in fact there is the possibility that the MOSA approach could increase development cost. And then the ability to incorporate innovation, and that's both innovation at the initial design side and later innovations. So it's across that life cycle. I moved on to chart 4, and now I want to talk about how we're kind of the framework and the foundation of this talk. Over the past couple of years, I've had the opportunity to be closely, to have close observation of a number of TARDEC initiatives, and one of the things that TARDEC has been doing in their advanced technology demonstrator programs is not only to develop, integrate, and prove out advanced technologies, so actually demonstrating them in an integrated setting for TRL 7, but also they're using these programs and projects as a platform to test and develop systems engineering tools. And I'll call this a learn by doing or develop by doing, realizing that we can't wait for tools to come kind of full-blown, and there are a lot of integration of tools and integration with ways of doing business, and the best way to, a good way to work this is to try working these in experimental programs. And so a couple of these are particularly relevant. One was an initiative where TARDEC implemented a form of modular open system acquisition, and we had some interesting observations from that. By the way, I do not intend to identify any of the specific programs or talk to them in particular. What I'm after is what are the lessons learned and challenges that we can extract and generalize from these programs. So in the one program that used an modular open system acquisition approach, there were some acquisition practices that we'll see, some architectural modeling issues, and there'll be some challenges there. The very interesting thing was that it appeared that a form of set-based design emerged from the MOSA organization, and that there was not an initial intent to implement set-based design, but it was something that we observed because of how the coordination in MOSA was going on. So we'll talk to that. One of the related findings had to do with model and simulation integration, model-based systems engineering, and how that relates to the MOSA initiative. This actually, the M&S integration and the movement towards MBSE and the digital thread is actually a part of a different advanced technology demonstrator program. But since that kind of integration is important for MOSA implementation, I wanted to draw on some of those lessons as well. So that's kind of where we're going, and now I'm moving on to chart 5. And I want to emphasize here the role and perspective of TARDEC and what I'm calling an Agile Systems Engineering Enterprise. And the reason is that the RDECs, Research, Development, and Engineering commands, have to deal with projects of a wide variety of starting points, a wide variety of constraints, a variety of endpoints. So these programs start at different stages of the acquisition life cycle. Some programs skip milestone A and enter at milestone B. There's a different kind of work that needs to be done. Some programs are starting at milestone A or pre-milestone A. TARDEC gets involved in that early concepting phase, all the way through past milestone C, where we get into upgrades. And the constraints on upgrades and new starts are very different. We've got programs that are from major defense acquisition programs, programs of record, as well as science and technology demonstrator programs. Some are responding to urgent operational needs, and some are part of very deliberate strategic planning in our weapon systems. And then all the individual programs have their own constraints, schedule constraints, time constraints, and acquisition strategies. And on top of all of that, the engineering organization intermittently gets reorganized to be more efficient and effective. And so all of this means that as a systems engineering enterprise, TARDEC and other RDECs like that have to be agile to adjust. And our kind of human-centric systems are very agile. We can form and reform and adapt as we figure out what the program is very well, but it has the limitations of being potentially unstable and forgetful and individualistic. So when we think about digital workflows using digital connectivity, this has the potential to represent and reuse knowledge about the workflow, but are also potentially brittle. And if these kinds of advanced systems engineering strategies limit the ability of the organization to respond to the needs that they get, the tools won't be used. The tools won't be relevant. So one of the big challenges for implementing MOSA, model-based systems engineering, and the digital thread, et cetera, are to support an agile systems engineering enterprise. And this is probably going to be a theme that I will come back to with more specifics. Moving on to slide 6. So when we look at those MOSA benefits in this context of a variety of systems and over the life cycle, I start thinking about how to implement MOSA in a way that will realize those benefits. And that's what these learn by doing exercises have been. And so I think that one thing that will help is to take those 5 categories of main benefits and then translate them into what are the realization challenges for MOSA. And so I think that going explicitly, looking at what that means during the different life cycle stages is important. One of the things that we've seen with TARDAC in particular is both mixed solutions. So for example, we might have a future combat vehicle that when we look at the missions for that combat vehicle, there's not going to be one vehicle that can meet all those requirements. So we might actually end up with a mixed solution that is I'll call it, for want of something better, a wheeled variant and a tracked variant, sharing some commonality in parts, sharing extensive commonality in communications and design principle, but actually ending up as with unique vehicles, with separate vehicles, but as part of that modular acquisition, that's still a viable solution. So we're not necessarily talking about a single design. Somebody might think about the F-35 Joint Strike Fighter in this context a little bit, where we actually have 3 variants. And I think the other piece that we want to talk about in thinking about acquisition strategies to rapidly adjust is how can we get natural incentivization of MOSA in the contracts as opposed to commanding certain styles of development. And I think what we will see in our one case study, or in one of the case studies, is where we had some of that natural incentivization. I think another point that we'll come back to a couple of times is that there's a certain infrastructure capability, an ability to deal with burdens such as weight and power requirements and physical size that are system level burdens. They're cumulative from the components, from the subsystems, and yet there are certain subsystems whose requirements depend on that total answer. And so we have some kinds of requirements that cannot be quantitatively reduced and allocated to individual systems. We can functionally allocate power to the engine. We can functionally allocate some weight aspects to a suspension, but what actually the quantitative requirements aren't known until the whole system is. So we get our whole strategy for decomposing, that reductionist strategy is challenged. And so that's going to come back and be an important issue in how we're able to get the, how that's improved by the MOSA approach. And I think those are kind of some of the main points. I think I want to just throw in a nice keyword from the bottom line there, which is that when we have a modular structure, when things can be added at the end or swapped out at the end, we get an opportunity for what's called delayed differentiation. And when we want to have the benefits of delayed differentiation, that is, we proceed with constructing 95% of the vehicle or 90% of that system, and then say, now when we're going to go put it in the field, we're going to finish it with the last 5 or 10% of add-ons that are needed for the mission that we're sending it out to. That's not just modularity in terms of the organization and the packaging and function, but it's also a modularity that's tied to the order of assembly and the order of integration, so that the order of activity is another basis that we might want to look at when we think about what are the dimensions of the system that are going to be used as the basis for system decomposition. So just coming back to one of the things that we do a lot of in systems engineering is we take a system and we try and break it down into parts so that we can build parts, define interfaces. And we know that this never works perfectly. There's always dependencies. We try and minimize the dependencies with loose coupling. We try and maximize the internal coherence. But because our systems are complex and have a number of different dimensions that we're concerned with, we might achieve loose coupling on some dimensions, but not on others. And so when we come back to the question of how do we implement MOSA to achieve those 5 main benefits, on the implementation side, we need to think about what are the architecture dimensions that we want to use for the primary organization of envisioning the system that will achieve the priority benefits. And it may be that there is no one answer that achieves all of them best, so different programs will have different priorities. Going on to chart 7, so I'm going to start talking about this, our first case study. And it was a TARDAC Advanced Technology Demonstrator Program. And systems engineering at TARDAC decomposed the system into 5 subsystems. They defined functional requirements and high-level interfaces. The 5 subsystems were picked based on a functional coherence, and also because there were different, there were vendors with particular expertise. And as an advanced technology demonstrator program, one of the things that TARDAC wanted to do is to advance those technologies, integrate them, and prove them out for TRL 7. So there were 5 contracts for the 5 subsystems, and 1 system integrator contract who was going to pull all these together into the final product. But there were no contractual relationships or obligations among those vendors. The integrator did not have any command voice or authority over the vendors. The integrator was just another team member. They used a functional composition to pick those 5 subsystems, and one of the things that they were able to do, a side benefit here, is that they were able to use an architecture based on their functional decomposition, as opposed to what often tends to happen, which is that the structure of the engineering organization ends up defining the architecture of the system. If I've got a department that does running gear and a department that does powertrain, I'm going to organize my my system would be organized into powertrains and running gears and communications or whatever. So Conway's law is that, typically the architecture of the system reflects the organization that built it, but this way they were actually able to circumvent that principle. They also, in doing this, realized that there were going to be dependencies, interactions, and interfaces across the subsystems that could not be anticipated at the beginning, and because some of these would depend on how those subsystems were developed and what it took to integrate them within a system. So rather than try and be overly smart and figure out all those dependencies and interfaces with all the possible variations, which would almost certainly be wrong and might constrain the solutions, what they tried to do was to get guidance and requirements for collaboration among the vendors to achieve mutually acceptable interfaces and standards with regards to the interfaces and dependencies. And that turned out to be a really interesting step. I'll go on to chart 8. And so it's because of that step that we saw that SetBased Design emerged from how the MOSA acquisition was set up. So in SetBased Design, we have design where we've got different groups with diverse interests that are ideally using the SetBased Design principles or approach to collaborate. And the thought behind SetBased Design is that there's a number of subsystem and component solution options. Those are all kept open until they need to be restricted for some reason. And the collaboration is balancing multiple viewpoints and priorities to incrementally restrict the design options. When they're restricted, these become narrow, and eventually there's a particular design emerges. So how did the MOSA acquisition lead to SetBased Design? Well, first, the vendors had to collaborate on either side of each interface or dependency. They had to agree on how the dependency would be handled or how the interface would be handled. And so they started with a kind of general, fairly open standards with the intent saying everything on each side of that interface that could live within that standard was still a viable option, and then the parties on either side of the interface would collaborate to say, how can we restrict or further specify or make precise these interfaces and dependency relationships with that would still that would not put the vendor at risk of not being able to fulfill their contract, so because they each had different contracts. So what happened was that the interface and dependency standards and definitions emerged kind of in sync with the refining the design concepts. When a vendor got to the point where it said, I cannot proceed further on developing my design, I've got some choices to make, but they have to be consistent. They're going to restrict the interfaces, which means there's going to be an implication for the vendors on the other side of the interface. That's when the decisions to further specify the interface had to be done, and by further specifying the interface, that restricted the solution set, the feasible solutions. So that became a point that drove the timing of when the decisions in SetBased Design were made to restrict the solution set. It's because the design could not go forward without that. And the way those decisions were collaborated or coordinated between the vendors was through those interface and dependency standards and their specification. So this actually solved a couple of the problems or ambiguities in SetBased Design, which are that there's not a clean theory of when those restrictive decisions should be made or the basis for making those decisions. But in this case, this set up a framework that incentivized the vendors to fall into a set-based design solution approach. We would note that the realization of this tends to be, and tended to be on this program and on others that have done something similar, that the interface and dependency standards are refined in very small incremental steps, which means you end up, it's holding back the design process. So anyway, this was the kind of the success and interesting thing, that the set-based design emerged from the MOSA implementation. Moving on to chart 9, I want to poke a little bit at what some of the bumps in the road or the challenges were in that case study. And so it looked like a beautiful can of worms from the outside, and when we look at the inside, it's a little bit of a can of worms. So the interfaces and dependencies were not independent of the design choices. So the separation, the coupling actually depended on the choices of design and were not inherent to the functional decomposition, but they depended to some extent on the exact solution. We already talked a little bit about the SWAP-C, size, weight, and the A is for and, size, weight, and power, and cooling, that's the C, which are system level requirements. They're allocated to subsystems that perform, provide the capabilities to meet those burdens, but the actual levels of those burdens depend on the integrated system. So for example, we saw on the, I'll pick on FCS because it's had so many good lessons to learn. We started trying to have initially with weight goals on vehicles that were 17.5 tons. But when we looked at the when all the requirements for the different subsystems and approaches were put out there, and the subsystem group said, here's our solution. Our solution, it weighed too much. So we said, fine, we'll add up all that. Here's the new weight goal. But that didn't work either, because at the higher weight, that said, well, now the engine has to be bigger, the suspension has to be different, we need different number of road wheels on the drive, and we're bigger, so we are going to need more armor, and the weight goes up, and you go through an iteration again. So there are, even if they're not entirely emergent properties, they're system-level properties. Progress was slow. There were small incremental collaboration agreements, and this is frustrating to a lot of engineers who wanted somebody to just make a decision, decide how we're going to do things so we can get on with the design, which was more or less the antithesis of the collaborative set-based design approach. So there was certainly a new learning curve for this way of doing business. Now we get to where things got a little stickier, which was that while there were requirements about the system interfaces, openness of the interfaces, and integration of the parts, that did not extend to the modeling and simulation tools that the vendors were using. Some degree of system-level M&S integration is really needed to see that all these parts are achieving the performance, when they're integrated, will achieve the performance that was expected, but the M&S tools were incompatible. They were not plug-and-play compatible at any rate, and there was no contractual requirement for that compatibility. So even when different tools might be dealing with the same general categories of information, power profiles, for example, or a mobility performance, different models, depending on what they had originally been developed for, had different types of inputs, different resolution, and different assumptions that went behind those models. So what ended up happening was that each vendor kind of did their own preprocessor to take what they could from other vendors to add other information that they needed to get the context right for one-way translations with whatever provenance resulted from that. And part of the related issue as to why these models were not shared or shareable is that the modeling infrastructures predated the contracts and often had proprietary knowledge about the modeling approach, the analysis approach, and sometimes the design as well, so that the models weren't covered since they were pre-existing IP. They were not covered under any exchange agreements. A recurring and potential problem that MBSE will have to address across the contractual divide. Going on to Chart 10. So I want to summarize what I saw as some of the challenges that emerged out of that case study. And a big one is the choice of the basis for system decomposition. So there was a functional decomposition, and physically the subsystems were fairly coherent. They were loosely coupled on some dimensions, but on other dimensions, especially logically, and the kind of computational and logic side, were more tightly coupled. So the question that I want to pose is, when we look at an architecture, when we do our system decomposition, how does that decomposition affect the ability to achieve those 5 MOSA benefits? And when we look at the different MOSA benefits and look at the priorities of them, what would that say about how the system architecture ought to be developed in the system decomposition? Recognizing that there's multiple architecture views, there's multiple types of dependencies and types of interactions across that whole life cycle for the vehicles, is there a way that we can more effectively integrate multiple architecture views into the system decomposition process? So these are good systems engineering research type questions. I also mentioned briefly the issues of model integration across the contractual divide. So sometimes we have the models that are used to develop systems actually end up being embedded in those systems. Control system models are a good case in point. And there's often proprietary knowledge and proprietary models of physical processes that go on in that. So how do we deal with that? That's a tough one. Is there a way to have that we can normalize and have responsibility for developing translators and interfaces between the models, if that ends up being the solution approach, which, given that the models have to be encapsulated to some extent to protect the IP that's inside of them, we end up with that kind of a model where there are translators or interfaces or plugs and sockets that are published and open while hiding the inside of the models. But somebody's got to be responsible for that, not letting it be kind of ad hoc and as needed. Related to that is, as soon as we get into the issues of translators and interfaces, when we know that the models might have had different assumptions behind them or different resolutions, is what kind of what's the metadata that we need provided and we need to go along with those models, and what's the provenance of that metadata that lets us at least put some bounds on how compatible those models are. When we talk, just looking ahead to some later topics in this talk, we're going to come back to the questions of compatibility of different models and assumptions across the workflow and the provenance of that data and what that says about some opportunities that MBSE might give us. And in fact, I think that's my next point, which is there's some opportunities to rationalize the workflow and reduce rework. But when we think of, so what I'd like to suggest another challenge is when thinking about model integration, model-based systems engineering, not only is what's the opportunity to rationalize the workflow, but how does that contribute to the different MOSA goals? And, so I keep coming back to when we think about implementation, let's think about implementation in terms of benefits to the different goals. So moving on to chart 11, just a little bit of a recap. That MOSA is going to depend on a system architecture model, which is the basis for decomposition. That's how pieces are divided up. So we need to think about that in a more comprehensive way for the benefits of different approaches. Set-based design is kind of is a means to an end. What we actually saw was that setting up MOSA correctly caused the set-based design to emerge. Are there other MOSA implementation approaches than this one case study? And if so, would they encourage set-based design? And how do different MOSA approaches contribute to those MOSA benefits? These are some open questions as we try and look towards implementations of MOSA. We'll see that the architecture model and the system decomposition impact the entire engineering workflow, and that models and simulation integration is a large part of the effort that goes on, simulation and combined analysis, in the engineering development workflow. So I come back to that architecture question: how does the choice of architecture affect the engineering workflow? At the engineering workflow level, we kind of come back to Conway's law, because typically it's different, I'll call them agents, but you can think of them as being engineers or engineering organizations or teams using tools and models, that these are the elements that do something. And they're organized, they've got tools, they know what they do. These are the pieces that flexibly reconfigure to be an Agile organization, shuttling models and data around. Some people build models and give them over there, and other people use them, and so on. But that organization is not necessarily driven by the architecture of the system. So there's some kind of rough interface there. And so I think that those architecture issues related to the organization and the systems engineering workflow of the organization are things that need to be tackled. So going on to chart 12, so we've talked about architectures, and I want to talk a little bit about the ground system architecture framework, which is a TARDEC initiative. And so TARDEC has seen a number of these problems. Maybe they haven't been thinking so much about MOSA, although they've thought about it to some degree over various programs, and certainly looked at common subsystems, common component strategies since FCS and before. And one thing that TARDEC has done is they've tried to take a more systematic and comprehensive approach to defining a framework for ground system architectures. So this is an ongoing initiative. It's evolving. It's gotten richer over the few years since I've been aware of it. And the idea is to get one more comprehensive framework for multiple uses that presents the multiple viewpoints, which combining both acquisition perspectives and technical perspectives, and that are combining the different dimensions of design. So we can have one architecture model, multiple viewpoints, along with modeling and architecture description guidelines. So a big part of this is the standard product classification hierarchy. Essentially, it's a breakdown of the system, a decomposition of the system, as an and/or graph. So at and nodes, it says if you've gotten to this point, if you've made these design decisions, you're using a tracked vehicle with a diesel engine or whatever, to decompose this at this point, there are certain subsystems that are required. That's an and node. But for each of those subsystems, there might be alternative choices and solutions. So those are or nodes. So we end up with an and/or graph that, in theory, is a all possible solutions. Of course, it's not all possible solutions because you will add in other nodes underneath an or node, and then those might create other required elements in the and, but it's an evolving thing. Still, when anything has a hierarchy, there's a governing principle for the decomposition. And it's not clear that that decomposition organizing principle really needs to be the same at all the levels. In fact, when we look at the standard product classification hierarchy, it starts out as a more functional decomposition, and as things get very specific, it becomes much more physical decomposition. So the challenge that's buried in there is, given that we have these different architecture perspectives, how should we use them in coming up with these architecture frameworks? And the architecture framework also tried to address the high-level dependencies and interfaces. So there are principles like physical motion independence lead to different configuration. There's space claims. There's different forms of energy and information transmission. And then there's interfaces and dependencies that actually combine multiple components. And so they've started to articulate that as part of this entire framework. I'm not going to go into it too much, although at the end of this briefing, I included a few charts from a TARDEC presentation on the ground system architecture framework. So if it's of interest, we can get into a little more detail. So on to chart 13. So I wanted to highlight what I saw as some of the systems engineering challenges. I've talked to one of them that there is not necessarily a unique solution to the standard product classification hierarchy, because there's different dimensions that it could be broken out on. And so however it's decomposed, we're going to look at, is it a comprehensive hierarchy, and in what ways are the components coherent and loosely coupled? But we could also address the question of, and in what ways are they tightly coupled and incoherent? And all that's related to what we use as the basis for the hierarchy. We don't really have good tools to assess the complexity of the architecture or gaps in the architecture for risk assessment. And so this has come up and been identified by NCOSI and NDIA as being an area where work is needed. It's a source of risk in system development, and we don't even know how to measure it. There's the compatibility between the architecture model, what the system is, and what the systems engineering workflow is that designs to that architecture. We've talked about multiple decomposition bases. The question for MOSA is, okay, modular open system acquisition, modular open system architecture. How can MOSA make use of the architecture framework? And maybe a different way to ask that would be, what is needed from or could be added, should be added to the architecture framework to make it more valuable for use in modular open system acquisition? Are there other viewpoints, other content that's needed? So I think as we look at MOSA as a development strategy, we want to look at the systems engineering tools and say, how do they contribute? How can they be advanced? Going on to chart 14, I want to talk a little bit about those issues from about operating across the contractual divide. And that's the contractual divide between vendors and between the government and vendors. And so we want to manage this so that we can ensure that M&S integration is part of the process, and that it actually can use the models as being deliverables instead of documents. So there's a whole lot that we can look through where we say, well, what are the kinds of things that the government should provide to vendors? What are the needs? What are the requirements? But also, what's the rationale for the performance? Not just what are the technical performance measures, but what's the rationale? And again, in this life cycle complexity, the TPMs often mix progress measures with system performance measures. and that can be a little troubling. I think one thing that's important, especially as we look at cyber-physical systems, which one of these test systems was, is that it's not just the performance, but what are the states, modes, transitions, and behaviors. At least for ground systems, this has not historically been a big piece, but our systems are much more cyber-physical systems now, so these are important. Moving on to chart 15, just looking at from the vendors to the government, what should we be asking for from the vendors? Detailed architectures on multiple dimensions. The M&S used to evaluate functional performance, to design trade space models, and the external interface and dependency models. SimStim, simulate and stimulate, is a strategy in testing systems and testing prototypes where there's a context model, and those are things that need to be delivered. And certainly IP constraints need to be identified because that's where model encapsulation is. On to chart 16. So some of the challenges across the contractual divide. Just consensus on what the vision of model-based systems engineering acquisition would be. What would we use for CDRLs and DIDs? There's still contracts here. CDRL, contract data reporting line item, CDRL, lowercase s, and the data item descriptions. So what should we use there in contractual language, and how do we verify and validate those CDRLs and DIDs? How do we deal with IP embedded in the models? Are there meta-model templates that we can use for those MBSE suites that will help ensure that they interface adequately? Commercial third-party tools and COTS components, always going to be a problem because they're pre-existing. So there's a number of challenges that have come up out of some of these studies. Chart 17. Let's see, I'm going to take a pause here, and because I think this was going a little slower than I had thought, and we've got about 15 minutes left. I know we wanted to save some time for questions. Mitchell, can you jump in and just say how much more do you want me to go in, because I'm now transitioning to the engineering workflow for model-based systems engineering, and I know we want to leave some time for questions.
Yeah, have you had questions come in? Because I've been monitoring my email and I haven't seen anything pop up other than just folks needing to access the slides.
Okay. Yeah, for some reason I lost my WebEx screen with the Q&A window, so I'm not seeing that.
Okay, and my Q&A window.
We did have two come in. Like Gordon mentioned, are you looking for existing programs on which to form case studies? So
we used a couple programs that were current programs. I think that case study programs are extremely valuable for us at the SERC to look at, because even though there's different ways of doing implementing MOSA, every experience is going to give us new insights and new challenges. So in these couple projects, I had several programs that we looked at. I think that going forward, if there are additional programs implementing MOSA or MBS model-based systems acquisition, those case studies would be very valuable.
Excellent. So hopefully, Nick, if you do have something in mind, you'll follow up with us. And then William Bishop asked, with teams putting decisions off to the last useful moment, did that complicate the system or the SetBased Design and MOSA, or did you take special steps to address the challenge?
So it wasn't really that decisions were put off until the last moment. Decisions were put off, decisions were made about, the collaboration decisions were about interface standards. So that was everything that was between the subsystems. And they were put off until one of the vendors said, I can't go forward without resolution of this issue. so it was kind of an on-demand.
Critical path.
Yeah, and so it wasn't that things were pushed off to the left intentionally. They were just when progress could not be made until they were resolved, then the collaboration had to make a down select decision, which impacted subsystems on both sides of the interface, since they had to now be they needed to have compatible solutions for the more restrictive interface and dependency standards. It was experienced as a delay in getting the engineering done. You know, there was a frustration aspect of it, but it was something that emerged from how the coordination was set up between the independent vendors that kept the options open.
Got it. I'm almost thinking that it would be good, since we're having some follow-up questions from some of the same people, if anybody wants to be unmuted to kind of discuss directly, please let me know. But we do have another follow-up from Nick of, is there a good reference for SPCH? I'm not familiar with this model. We use a different model in shipbuilding, the SWIBS.
Okay. So at in the backup slides on this presentation, there is a few slides that I extracted from a TARDEC NDIA presentation on the ground system architecture framework. That entire presentation is downloadable, and I believe there's a paper that went along with that. And the authors are identified. So I would say, so the answer is yes, there's a reference, and I'd suggest looking at starting with the presentation that's at the back of this slide deck.
Yes, actually, I will have to re-add that because I did remove the backups.
Okay, I wondered.
Back in and add them to the website. Also, Dan mentioned, no doubt that risk management tools are often inadequate to address or not well synced to what's being produced within architectural frameworks to get the level of risk management that is needed. What would those tools look like?
So I think there are, so that is not an easy question. There are certainly kind of simplistic points of view of architecture complexity. You can say, well, how many nodes and how many links have we identified? Well, that at least tells you something more than nothing. I think that it's more interesting to look at the dynamics and the evolution of the architecture, how stable it is, or how much, and the rate at which it's being refined. So that might be one way to look. The DARPA funded a program called META, and I guess they had a second phase, META 2, that looked at a number of different tools. And they had multiple awards to different vendors who were trying to look at measures of complexity of cyber-physical system design. Some of the people tried to take DSM approaches, design structure matrices, and measure complexity from those, but there were problems when there were loops and things were not just one directional, so the actual computations failed. But they had tried to take a kind of a theoretical axiomatic design approach. I think it does depend on the level of detail at which you try and use those axiomatic design measures, because things just become huge, and if you get down to the nuts and bolts level. There were other approaches that were kind of unsatisfactory to me that just said, well, here's a bunch of things that we can measure. We don't know if they're any good or not, but we'll evaluate them on a couple of hundred different programs, and we'll see which ones are, we'll do a principal components analysis and see which related to which, and see which of them seem to be related to cost and factors that seem to be resulting from complex designs. but they did not come up with consistent answers when they used different input data sets. So that approach did not look too promising. But I guess that's what I can say about those kinds of tools from the extent that I looked at them.
Great. And then from Robert Keene, how can these methodologies be effectively implemented within the rigid phase gate acquisition process?
It's really not such a rigid process. I'll give a simple, a case in point. The Armored Multi-Purpose Vehicle, AMPV program, was a New Start program, and it entered at milestone B. So if we can skip the entire technology development phase in the life cycle as needed for the program, I think that's an indication that there's a range of flexibility. I mean, what I have found is that the life cycle model, although it looks rigid, really does accommodate a great deal of flexibility to the engineering organizations. There's certain divisions when things are handed off to contractors, but even there, different programs can have different levels of continued government involvement and different levels of, of further architecture development. But I think that's simply something that takes some work, but I think that I don't see the system as being overly rigid.
Gotcha. And he followed up saying, I still strongly believe that outfit density and power density are valid measures of complexity for early stage design.
So density is a great one. And, we've talked about this in the ship context, power density. And, I took that notion and said, it's not just energy density and power density. We can look at a lot of those other dimensions that could be the decomposition dimensions and say, what kind of density do we have? What's our information density, right? And what's our communications bandwidth density? And I think the notion of how much are we trying to pack into a small box is probably a pretty good measure of how hard things are going to be. And so it's power and energy, but it's also information and how much functionality are we trying to pack into this small box. Where I see there's an interesting question here, though, that comes back to the MOSA approach, because if we're organizing things in this modular structure, then we have to leave room for interfaces and replacement. In some sense, we are going to be decreasing the density, and actually, we're actually doing even more, which is that we won't talk about, say, density over the entire ship. If we've got a compartmented design of the ship, we can talk about the density, energy density, information density, et cetera, of each compartment. In ground vehicles, we often divide the compartments based on the motion relative to each other, or isolation from some factor like noxious exhaust or whatnot. So once we end up with these kinds of compartments, we can talk about the complex, if that's the basis for the architecture design, we can talk about the various densities that we're trying to pack in. So I think that density is a useful and fairly intuitive measure of kind of how hard we're making things. I think we can also look at the density of interfaces and dependencies. That kind of gets back to the axiomatic design model. So thanks for the comment, Bob.
Oh, and then another question from Daniel Canales was there any regular synchronization form, scheduled or unscheduled, for the developers and their compatibility concerns?
Oh, there was, quarterly reviews, but that was more of an administrative thing. The real goal was to have collaboration as it was needed, being driven by design progress. So it was really more of an ad hoc collaboration as needed.
Excellent. Agile, if you will. Yeah.
Exactly.
Great. That's all the questions that I've seen fielded. And again, if anybody would like to speak directly, feel free to let me know and I'll unmute directly. But I don't know, Mitchell, did you have any questions that came in?
No, I did not, through email. So again, thanks for those on the phone for joining in. And I would like to take the opportunity to greatly thank, on behalf of the SERC, Dr. Gary Witus, for his presentation and SERC talk today. And of course, the slide package is posted on our SERC website, so that's sercuarc.org, for those who would like to download their own copy.
Oh, and I will be adding in those additional backup slides.
Yes.
Oh, there is, it seems, one question from John Taylor, actually. Sorry to cut in. John, I'm just going to unmute you because I don't see the actual question listed. But you're unmuted, so feel free to ask directly.
Okay, thank you very much. Gary, I was just wondering what was the technology basis of the collaboration interface and dependency standards and definitions, please?
You mean what tools were they using?
No, more in terms of what were the interface definitions, technology. Are you using a specific interface standard or some various interface standards? Or?
So there was a reference to ISO standards, this, that, and the other thing. I don't remember those, and I didn't note that. But so these were. So once again, these were standards that the vendors had agreed on and the government had approved, and it was basically they were working from ISO interface standards, which are of course fairly general to be able to be tailored for different specifics. I don't remember what the particulars were.
So maybe AP 239, something like that.
Right.
Okay, thank you.
Okay, I have one quick question for Mitchell. I'm looking at the upcoming topics, and February 1st, Grady Bush is going to be talking. This is the same Grady Bush that wrote, what, object-oriented design many years ago?
That is correct.
Oh, great.
The Grady Bush. So please, for those interested, of course, we have a CERC talk before that, and that information is also posted online. But yes, we have a great agenda of upcoming CERC talks. Obviously, not to marginalize anything that you presented, Gary, because this is excellent. But we look forward to participation by those folks who joined today, as well as disseminate the information. We want to make this widely available to everybody.
Okay, so I'd like to make one closing comment. I'm sorry that I didn't get to the second piece of this, which was talking about analyzing the modeling and analyzing the engineering workflow and developing data provenance models for model-based system integration. There's some interesting work there, and we may get a chance to talk about that at a later time.
Okay, excellent.
Okay, thank you all for listening in.
Yeah, thanks so much, Gary. Appreciate it. And thank you all.
Okay, thank you all. Bye.